Well, this is the actual name of the talk. If you see your schedules, you will see that the guys of the SL already optimized the name of the talk because it says bytecodes. Okay, my name is Guillermo Amaral. It sounds like Brazilian, but I am from Argentina. And I work for Season Systems. And I will talk a little bit about the work we've been doing regarding bytecode optimizations. First of all, I'd like to point out that even though we had in mind some optimizations, our main focus was not on implementing those optimizations, but in understanding and documenting the process of compilation in general, and in particular the process of optimizing bytecode generation. So as everybody here might share the same opinion, the best way for understanding, exploring a given domain and documenting the knowledge gained is by means of a Smalltalk, so we did it using a Smalltalk. This is just a glimpse of the 3 different levels of code we have involved. This VM contains a just-in-time compiler. That is, it is not an interpreter VM. So in the first level, we have Smalltalk code. This is a simple method in which, well, we define a temporary variable and then we use it. You use it as an argument of a message. And then we have the bytecodes corresponding to that method. For instance, we can see that the first 2 bytecodes correspond to the assignment, and then the following bytecodes correspond to the message send. This translation takes place at the image side. And then we have another translation that is from bytecodes to machine code, native code. Here we see machine code, and in fact, we can see the association between bytecodes and actual assembly code. So a couple of words about the architecture of the VM in which we've been working on. This is a particular VM, but is related or based on Digital's VM. It basically follows the model proposed by Alan Werfbrock in this paper, except for some differences. I will say what they are. This architecture consists on a few, in fact 2 special purpose registers plus a stack of frames, that is activation frames. And this stack is the same native stack. And as I said before, it contains a just-in-time compiler. This is just a snapshot of this architecture, in which we can see that we have 2 registers, register R, in which before sending a message we have to load the receiver, and it will contain the result of the message sent. And also we have another register, which is the A register, that it will contain, in some special cases, the argument of a binary message send. In the paper of Alan Werfbrock, this is used always for the last argument of a message. But in this particular VM, it is only used for special cases. So, well, this is just a reduced picture of a stack frame in which we can see, well, the arguments of the message here. Also, we have, well, pointers to the calling or the sender, which is the preceding stack, and pointers to the compile method and to the environment, and also we have the temporary variables of the method on top of the stack. Well, speaking specifically about optimization, well, the first aspect is why. Well, the first reason is the most common reason, which is for performance issues, like well, reducing processor cycles and memory, unnecessary memory accesses. But also, there is another reason, which is simplicity. If we get simpler bytecode results, I mean, if we get simpler bytecode list, we can assume that we will get better results in the nativization, that is the native machine code generation. It will depend, of course, on the just-in-time compiler, but we can assume that. In fact, we also developed the just-in-time compiler, so we know that. But for us, as I said before, it was very much more important to end up with a kind of lab in which any small talker can play with bytecodes and, I don't know, test their own optimizations. This is very important for us. In fact, it's the way we find to share our exploration in this particular domain. Sorry. Oops. Okay. And this is also related to accessibility, which is basically the same. That is, make this domain accessible to any small talker, and not only for specialists. By the way, I think these two guys are the same. It's just a feeling. Okay, regarding about the way in which we implemented this. This is just a big picture of the compilation process in which we find, well, the input, which is source code, and then after the parsing phase, we get an AST with some decorations, suppose. And then this is directly encoded into bytes. These are the way, for instance, in which Digitalx perform this translation. So we can insert in the middle of these two last stages the generation of bytecodes, that is, create objects for representing bytecodes, then we can optimize them and finally translate them into actual bytes. And the important thing here is that this can be time consuming because we are creating objects. But first of all, it is done at compilation time, so we can afford that. And in the second place, we try to reuse instances of bytecodes that can be reused. For example, think about, I don't know, load nil. Load nil is a bytecode that can be reused in every compilation because it has no parameters. Well, finally, speaking about what to optimize. Well, bytecodes, as you might know, are divided in several groups or classes. One of them is loading bytecodes, which are in charge of loading an object into the register R for sending it a message. So suppose we have this simple method in which we have a temporary variable, we assign them number 10, and then we send it a message. Well, these are the bytecodes corresponding to that method. And if we observe, well, the first two correspond to the assignment, as I said before, but the third bytecode tries to load the object pointed by temporary t into the register R. But the second bytecode guarantees that t is already in R, because store bytecodes stores what it is in register R into some destination variable. In this case, is the same variable. So after store temporary t, we are sure that we, under certain conditions, we will see that t is already in R. So what we can do, we just drop this bytecode, and well, if this bytecode corresponds to some, let's say, assembler instruction, we will have one less of them. So, but as I said, it is really important to carefully analyze every possible execution flow, because we have jumps. Jumps are bytecodes that are used for controlling the execution flow. So, for instance, if these are a method in which we have the same situation as in the previous method, but we have jumps that land here, well, we wonder if t is in R at this point. Well, we have to analyze all the possible execution flows and see if the bytecode preceding every jump guarantees the same, that is, that they leave t in R. If that is the case, we are sure that we can actually remove the low temporary t bytecode. Well, another kind of optimization is related to push bytecodes. Suppose we have push bytecodes are used, as I said before, for pushing the arguments of a message on the stack. Suppose now that t is used as an argument of a message. So again, we have bytecodes corresponding to that method. And in this case, the first two correspond again to the assignment, and the following correspond to the message sent. In this case, we have one bytecode, which is load self, which loads the receiver. Then we have the push of the argument, and finally the actual send. But don't
try to save again.
I'm not trying to. Okay, here we go again. We have only a couple of minutes. Okay, regarding about the semantics behind the message send, from the Smalltalk point of view, we have to honor these steps. They are first evaluate the receiver, then evaluate the arguments in order, and finally send the message. This is a must. But from the bytecodes perspective, we, under certain special conditions, we can switch between the first step and the second one. That is, we can push the arguments before loading the receiver. So if we are sure that we can do that, in this case, we can switch between the load self bytecode and the push temporary. And what will we get is that push temporary T is behind store temporary T, which, as I said before, guarantees that T is already in R. So in this case, we cannot drop the bytecode because we must push the argument, but we can change this bytecode by another one, let's say cheaper than this, because this bytecode is translated finally to push in machine code accessing to memory, while if we know that T is already in R, we can use directly another bytecode, which is push R, which we, from a conceptual point of view, can assume that is cheaper. That is, we are accessing to a register instead of a memory. Well, and that's what we actually do. We switch the two bytecodes, and then we change the first one for a push R, which is a push of a register. But again, we have to analyze every possible execution flow because we are not sure. The fact that the previous bytecode guarantees that T is in R doesn't means the same for every execution flow. And the example deals with temporary, but this applies for every load and push bytecode because we have push temporary, push instance, and so on, push argument. So the same optimization applies to all the family of bytecodes. Finally, we have the jumps family, and suppose that we have this simple method. As you already might know, messages like and if true are aligned. That is, they have their corresponding bytecodes for controlling the flow. And well, this is rather obvious. Instead of jumping, we have two jumps, conditional ones, and of the same, let's say, the value, they are false. They will jump if there is a false in register R. So instead of jumping from 2 to 6 and then to 11, we can directly jump from 2 to 11, because if we have a false in register, that will be the final result, even though we leave it in this way. So that's what we do. And but again, it's not so simple, because first of all, we can have a combination change of jumps combining different kind of jumps. Like in this way, we have in the chain of the left, we have a combination of two conditional jumps with an unconditional one in the middle. So in this case, we are sure that we can patch the first two, because if there is a false in register R, we will jump and then unconditionally jump to the following, which also will jump because we have a false, so we can patch the first two, so they jump directly to the destination of the last one. But in the chain of the right, we have, for instance, a combination of conditional jumps from two different kinds. But in this case, what we can conclude is that if there is, in fact, a true in register R, we will jump to the first, from the first to the second, then to the third, and then we will jump, if we don't optimize nothing, we will jump to the last them of the conditional jumps, but since we have a true, we will end up in the following bytecode. So we can patch the 3 tests jump through bytecodes, so they jump directly to the next bytecode. I mean the bytecode following the last of them. So, well, I go a little fast with this. This is a snapshot of a big picture of the compilation process. Here I wanted to optimize, to emphasize the main objects involved in the particular stage of bytecode generation. We have, again, source code. This is parsed, that is, this is converted into a syntactic tree. Then once we have an AST, it is passed to the following stage. Here we have the bytecode generation. We implemented it as a visitor. This guy will generate bytecodes given an AST, but since there are two kind of optimizations, the ones that should be done during the bytecode generation and another that can be done right after we have okay, the last one, progress. Okay, this guy will cooperate with the bytecode optimizer, and we decided to decouple the responsibility of analyzing a list of bytecodes from the actual optimization. So we implemented another guy, which is the bytecode analyzer, which is in charge of answering questions such as is this variable in register R at this point, or something like that. Information will be used for the bytecode optimizer. Will based on that information will change. For instance, from one bytecode to another, will drop some bytecodes and so on. Well, finally, we will get a list of bytecodes optimized, and then we can pass this to the next stage. In this case, we implemented another object in terms of our using the bytecode pattern, visitor pattern, and this object will actually will do the translation from bytecode to bytes. Well, once we have the bytes, we can proceed with constructing a compile method with those bytes. So the main objects involved in this framework, of course, we have a complete hierarchy of bytecodes. We implemented also a bytecode parser using petit parser. This is very useful for various purposes. For instance, not only for printing already compiled methods, but also to implement queries about methods such as accessor to instance variables and so on in terms of our bytecodes. So we have the bytecode generator. We also have a printed bytecode visitor encoding. We saw this before. Well, we have a special optimizer for particular optimization, or we have the bytecode analyzer. We saw this, and we have two more objects. The first is a simple object, which is called Bytecode Optimization Analyzer, which is in charge of giving a bytecode optimizer and a set of methods. Just tell which of those methods are optimizable. And then we have a bytecode optimization benchmark for benchmarking purposes. This guy basically compiles one method, a given method, without the optimizer enabled, and then evaluates the method several times, and then it does the same, but with the optimizer enabled. So it provides, after this process, some statistics. For this, we disabled the GC because we wanted to have confident measures, but after the talk of Boris, we were happy before the talk of Boris, but we might change the way we measure, because it's very important what Boris said. Okay, some results regarding load optimization. We run the first analysis, that is, we from our image, which contains roughly 110,000 methods, almost 17% of them are optimizable, and the most optimizable method, which is the one that has more loads to be removed, contains 19 bytecodes, or loading bytecodes. So here we have two histograms of averages using the bytecode optimization benchmark. Since we run very much times, we expected to find a normal distribution here, but as you can see, we have several outliers, that is, measures that are very far from the mean of the sample. So here, both histograms seem to be overlapped. There is a little shift of the green curve, which corresponds to the optimized version. But then we apply a statistical tool which is called bootstrapping. Basically consists on resampling the sample we had before. But using this tool and the same data, we obtain this. This is the behavior of the mean of averages we saw before. And here we can clearly see that the optimized version is faster than the non-optimized one. Okay. Well, we have the same results for push optimization. In this case, almost 9% of the methods were optimizable, and the most optimizable one contains 11 push bytecodes to be changed. Here, the overlapping is more notable, but running again the bootstrapping, we can see that there is a difference, even though these optimizations seem to be less significant than the previous one. And finally, the jump optimization. Well, in the same image, we have less than 3% of methods which are optimizable, but here we see in the first chart that there is already a difference, a significant difference. And if we run the bootstrapping, we clearly see that this is a very significant optimization. So to conclude, as I said before, we find more interesting and important than implementing a couple of optimizations to implement a framework in which we can continue trying with new optimizations and also share this framework for another small talkers to try with them. So that's it. Questions?
Okay, there's a lot of ways you can optimize code. You can optimize the high-level code when you're writing Smalltalk. You can write pretty crappy code also there, and then you can try to optimize the bytecode of that out of that. But you could also optimize the high-level code. Have you any idea what makes the most sense?
I guess all of them.
Yeah.
But what I can say is that some optimizations at high level might impact on low level optimizations and some not. For instance, the analysis for changing the order of the message, the bytecodes corresponding to a message sent requires a high level analysis. That is analysis which is done in the AST. If we don't do that analysis, we can proceed with some optimizations in the low level. So I think it will depend. Any other?
So you you did static optimization on the compile time.
Yes.
So what would be your guess if you do the dynamic optimization at runtime? So would that be more significant than the compile time optimization, or the other way around?
I think that these kind of optimizations will be more significant in a static way than in a dynamic one. But,
because the overhead optimization.
yes, we are creating objects. That's it. Well, thanks.